So yeah, so going over this, right? When a frog jumps upwards off of a lily pad, which way does the lily pad move, right? Because of the third law that we learned yesterday, for every action there is an equal and opposite reaction. So the action is that the frog is jumping upwards. So the reaction must be the opposite of what the frog did. So the lily pad must move opposite of upwards, which is downwards. All right. Then finally, you push forwards against a wall. Which way does your body move? Right. Assuming if you're sitting in something or standing on something that rolls, you will move backwards because again, the action is the pushing forwards, and your body is going to move in the opposite to your actions, so backwards. Yeah, thank you for the illustrations. Yeah, that's how we do push-ups, guys. All right, so moving forward, just some disclaimers again. Please do not share any personal information during class. Your participation is vital, and we will keep calling you if we don't see any. And one final disclaimer that these Class Connect sessions are recorded for educational purposes. All right, we are on week 4 of 13. We are right smack in the middle of this week, so we're on Wednesday. We're going to be learning about how objects go into free fall. All right, we've covered all 3 of Newton's laws, so we should be able to apply those to talk about some more advanced motions. So, for example, free fall is going to be one of those. Specifically, we will be able to define and differentiate between mass and weight. We're going to learn the difference of those. We're going to describe the effect of gravity on objects in free fall based off of Newton's second law. Remember the force equals mass times acceleration, but we'll go over that. And then calculate the velocity of an object in free fall on Earth, and then we will show this by getting 80% or higher on our quizzes.
All right, so your notes are in the chat. Links are there. Go ahead and raise your hand once you have your notes open and ready to go. I'll go ahead and give you 20 more seconds. I do see a lot of you have already opened that up. 20 more seconds. We do need 100% participation. So either raise your hand, or if you're on your phone, send us a chat so that we know that you have your notes open and ready to go. All right, so what I want to know is, based on what you've seen on TV, is it easier? Do you jump further on Earth or on the moon? Tell me in the chat box, think about what you've seen on TV or in movies. Is it easier to jump on Earth or on the moon? There we go, getting some answers there, getting some mixed answers. Looks like most of us are saying similarly. Yeah, it's actually easier to jump on the moon. If you ever see astronauts on the moon, they're wearing a ton of like stuff because they're in space suits, and yet they can still jump really well. They can jump far distances. They seem like they're almost floating in the air. Smiley faces or emojis in the chat box if that makes sense. Again, they seem more floaty on the moon than on Earth. So it's easier to jump further on the moon. Now, based on what you've also seen on TV, right? What happens to an astronaut when they're in outer space or in zero gravity environments? So, for example, on the International Space Station, why do they need to like tie themselves down to things? Because what's happening to their bodies? Thank you, Kalina. Thank you, Amari. Yeah, they float, so they don't even touch the ground. So when you're in outer space on a vessel in outer space, or when you're in a zero gravity environment, which we can simulate on Earth, you actually float. Yeah, pretty crazy to think about, right? So here they actually float. Excellent. Now, what I want you to think about is, physically, is the person actually changing? Is there something that's physically changing about the person in each of these different environments? Tell me in the chat. Excellent. I see Amari in the chat. Think about, is the person's body changing? No. So there's something else that's going on, and we're going to go ahead and take a look at that today. So no, their bodies are staying the same. So we need to think about, why is it that their bodies can stay the same, but depending on which environment they're in, these different things happen, right? Earth, it's harder to jump. Moon, it's easier to jump. And in outer space or zero grav, jumping is just floating, right? You're just floating. Excellent. Let's go ahead and talk a little bit about that. So here's the deal, y'all. We talk a lot about these two terms in everyday life as synonyms, mass and weight. All right, but they are actually, in according to our physics definitions, they are not the same. Okay, so mass is what you are made of. Mass is your matter, like physically what you are made of. And so you have the same mass no matter where you are in the universe. So, for example, all right, if you weigh, right, 60 kilograms, then whether you're on Earth, on the moon, or sorry, if you have a mass of 60 kilograms, whether you're on Earth, on the moon, or in outer space, you will always have a mass of 60 kilograms because that is the stuff that you are made up of. Go ahead and give me a smiley or an emoji in the chat box if that makes sense. All right, so if you're 60 kilograms, you're 60 kilograms everywhere. All right, because that is a measure of mass. Weight, however, actually does change, and weight actually includes both your mass and your gravity. So weight is how gravity affects mass. So you have to include both of them when you talk about weight. All right, so based on your mass as well as your gravity, your weight can change. Weight is also known as the force due to gravity. Weight is an actual force. And so this is actually measured in newtons. So it's measured in newtons, or for example, on your scale, it would be measured in pounds. So weight or your force due to gravity will change based on your acceleration due to gravity, based on how much gravity is in that place. So that being said, this should now make sense based on our brainstorm. Earth has a lot more gravity, and so you weigh more. However, you still have the same mass. You're still made up of the same stuff. It's just harder to jump because you weigh more. If you go over to the moon, you suddenly have a ton of weight loss. So that's pretty cool. But you actually do still have the same mass. You're still made up of the same stuff. You just weigh less because there's less gravity pulling you down. And this is cool if you are in outer space where there is no gravity, then you actually weigh nothing. You weigh 0 newtons, even though you still have the same mass. You can see down here this example of our astronaut. So the weight on Earth is 560 newtons, which is way more than their weight on the moon, which is 92.59 newtons, because the moon has less gravity. However, regardless of where they are, even in outer space where they weigh nothing, their mass will be the same. Their mass is always 56 kilograms. Go ahead and give me a smiley, medium, or sad face if that's beginning to make sense. You should see that popping up on your whiteboard. Mass is always the same because you're always made up of the same stuff. You don't cut off your limbs when you go to outer space, hopefully. All right, but your weight can change based on what's going on with gravity. Excellent. All right, looks like we are all feeling comfortable with that so far. Let's go ahead and fill in number 2. This is number 2 in your notes. Go ahead and fill in the blank with the word acceleration and only the word acceleration. Make sure you spell it correctly, otherwise the computer will mark it as incorrect. So based on gravity, the acceleration due to gravity, your weight will change. Go, 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 raise your hands.
All right, so doing a little more practice about mass versus weight. Our whiteboard tools are on. Let's use our box tool to put a box around the appropriate response that finishes this phrase. Weight is based on what? Is it only mass, only gravity, both mass and gravity, or neither? So we have this little graphic to help us remember, right? So weight is encompassing the object and the force of gravity. Awesome. Yeah, it's a bit of a really heavy hint right there, but we're doing it on purpose because we want you guys to really get this ingrained in your memories, because this is like one of the most basic concepts that we need to use to understand everything else. Yeah, we gotta practice. All right, very nice. Yeah, so for number 3, please be sure to mark both mass and gravity in your notes for number 3. I will set a timer for us, and please raise your hand for number 3 when you are ready to move on.
Perfect. Okay, so let's go ahead and actually begin to apply this. So this one is a complete on your own, but we can start to break it down together. So don't put answers in the main chat, but if you want to check in with us, we're in the Q&A chat. So on planet A, an astronaut has a mass of 65 kilograms and weighs 233.35 newtons. On planet B, the same astronaut has a mass of 65 kilograms and weighs 576.55 newtons. So we want to know which statement is correct. So both planets have the same gravity, Planet A has more gravity or planet B has more gravity. Again, remember that weight is related to gravity. So we should be looking over here. Weight is related to gravity. That should help you out. If you need even more help, you can always look back at your notes number 2 again. Remember, mass is the same everywhere. So we want to focus on weight when we talk about gravity. Go ahead and answer question number 4. We'll go ahead and give you 30 seconds. Again, don't put answers in the main chat, but if you want to check in with us, we're in the Q&A area. Go, go, go. All right, let's go ahead and move on. So next brainstorm, I want to know, if you drop a brick and a feather at the same time, which one hits the ground first and why? Go ahead and tell me in the main chat, which one do you think will hit the ground first and why? Excellent. I see Angelina. I see Amari. Cody. And even if you have a similar answer to someone else, that's totally fine. You should still type it in and submit it because that helps you to reinforce your own learning and to think through it yourself. Yeah, so it looks like a lot of us are saying brick, and it looks like the main reason that I'm seeing a couple different reasons, is that it's heavier, all right, that it weighs more, and that it's not aerodynamic. It has more mass, all right. I'm not saying all of these are correct. There are actually some correct answers, some incorrect answers because of weather. All right, well, I would actually say that the brick definitely hits first. All right, if you've ever dropped a feather and a brick at the same time, a brick will definitely hit first. It's not for the reason that you think though up here though. So all of these reasons are actually not exactly right. So it's not for the reason that you think. It's not because the brick is heavier or weighs more. The brick is actually is actually more aerodynamic than a feather. And it's not because it has more mass. So let's go ahead and think about, why does it hit first if none of these things are true? All right, so here's the deal. Objects in what we call free fall, meaning that we're not affecting them at all, they're just falling, are only affected by the force due to gravity, by gravity. This means anytime we have a force, we have an acceleration. And since they're only affected by the same force, they all have the same acceleration. So same force of gravity equals the same acceleration. Give me a smiley face or an emoji in the chat box if that makes sense. Forces cause acceleration. If we have the same force, we have the same acceleration, right? Okay, now that acceleration is a rate. So they are all accelerating at the same exact rate. And the rate of gravity, acceleration due to gravity on Earth, is always negative 9.8 meters per second squared. Negative because it's going down, okay? So what this means is if they all accelerate at the same exact rate, then everything should hit the ground at the exact same time. So how many of you have ever seen a picture of the Tower of Pisa or heard about Galileo Galilei's Tower of Pisa experiment? Yes or no? Tell me in the chat. How many of you, I have either seen this, I've actually seen this in real life. It's super cool. Yeah, so what Galileo Galilei did, or supposedly did, we don't actually know if he went to the top of the Leaning Tower of Pisa, but he did figure out that if you drop something that has more mass, like 1,000 kilograms, with something that has less mass, 1 kilogram, then they actually do hit the ground at the same exact time, okay? Yeah, the tower is weird. It's sinking because of not being built on a very structurally sound ground. So the question then becomes, why did our brick and our feather not hit the ground at the same time if everything should hit the ground at the same time, if they're only affected by gravity? So we're going to go ahead and see an experiment about why this happens. This is one of my favorite experiments. I'm going to go ahead and show this to you up on the whiteboard. I'll also share it to you in the chat box if for some reason it doesn't work on the whiteboard. So let me go ahead and show this to you up here. Sorry, just going to move things around really fast.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant.
All right, isn't that amazing? I know. How did that even happen? Okay, so in the first instance, when we did have air in the chamber, which one hit first? All right, so when we had air in the chamber, which one hit first? He dropped the bowling ball and the feathers at the same time. In the first example. Yeah, definitely the bowling ball. So he said the reason the feathers don't fall at the same rate is because of something called air resistance. So we're going to talk about that in just a few moments. But he did show that if you remove all the air, then in the second instance, which one hits the ground first? So the second time, which one hits the ground first? Or hits the box first? Tell me in the chat. Yeah, they actually hit at the same time. So this is exactly what Galileo Galilei was saying, was that regardless of their mass, whether it's a feather or a bowling ball or a brick, regardless of their mass, they should always hit the ground at the same time if they're only being affected by gravity, because they all should have the same exact rate of falling. Smiley faces emojis in the chat box if that's beginning to make a little bit more sense. All right, so this is actually true. It blows your mind, but this is actually true that regardless of your weight or mass, regardless of your mass, you should always hit the ground at the same exact time if you're released from the same point. Okay, now again, the reason he said it didn't work the first time is because of air resistance. And the reason why is because air resistance is actually another force. Right, so let's go ahead and take a look at that right here. So air resistance is that reason or that exception why this didn't work the first time. So, and that's also why we intuitively know bricks hit the ground first. So air resistance acts as a second external force that opposes motion, which reduces that feather's acceleration, which is why it doesn't hit the ground at the same time as a brick in normal real life. But again, if you ignore all other forces, air resistance, etc., and there's only gravity, then no matter how much mass you have, you will always hit the ground at the same time. You'll always have an acceleration of negative 9.8 meters per second squared, and therefore you will always hit the ground at the exact same time. All right, go ahead and give me a smiley medium sad face if this is beginning to make sense. Again, we're going to practice it in just a moment. I know it's kind of, again, it blows my mind every time I see it. Like, I know why it happens, and it still is so cool. Go ahead, smiley, medium, sad face. Matthew, Jonathan, Alan, Brianna, Joseph, Callie, Amari, Kamal, Seraphim, Jalen. How are we feeling about that? Again, no matter what it is, it will always have the same acceleration on Earth, negative 9.8, and it will always hit the ground at the same time, assuming there's no other outside forces like air resistance. All right, let's go ahead and actually practice this together then. Sorry, I lied. Let's go ahead and fill in number 5 first. So fill in the blank with the word same. Again, same rate, same falling, same, hitting at the same time. That's 20 seconds to fill in number 5 and raise your hand. Capitalization does not matter, but spelling does. All right, let's go ahead and move on and actually try this out. All right, so on the whiteboard, I want to know, what is the acceleration due to Earth's gravity on a 20-kilogram ball? Again, we just need to remember, what's that special number? What is the acceleration due to gravity? Go ahead and box it on the board or tell me in the chat. Box it on the board or tell me in the chat. Thank you. I see Mallory up on the board. Let's get some more participation. Awesome, there we go. Let's get our answers up there. Perfect. Yeah, so absolutely, the acceleration due to Earth's gravity on a 20-kilogram ball is the acceleration due to gravity, which is negative 9.8 meters per second squared. So similarly, what is the acceleration due to gravity on a 200-kilogram ball? It's still the acceleration due to gravity, so go ahead and circle the correct answer up on the board. What should still be the acceleration due to Earth's gravity, even on a 200-kilogram ball? Get your answers up on the whiteboard. Excellent. Yeah. So if they have the same acceleration due to gravity, so now looking over here, both objects, 20 kilograms, 200 kilograms, they have the same exact acceleration due to gravity. So they should have the same rate of falling. They're in free fall. There's no air resistance, no other things going on, just like in our vacuum. Then, according to our experiment and according to our concept here, which object should hit the ground first? The 20 kilogram, the 200 kilogram, they hit at the same time, or neither of them hits the ground? That last one's kind of silly, but go ahead, get your answers up on the board. Again, just like in the vacuum, think about the ball and the feather in the vacuum with no air. Even though they have different masses, which one hits the ground first, or do they hit at the same time, or do they never hit the ground? Get your answers up on the whiteboard. Go, go, go. Yeah, they should actually hit at the exact same time. Again, if there are no outside forces, no air resistance, like with a feather, then everything hits the ground at the same time because everything is only affected by gravity in free fall. Excellent job on that one, everyone. This is going to be the answers to 6, 7, and 8. Go ahead and check those off for me. You have 30 seconds to get those done. Raise your hands. Go, go, go.
All right, so just learning and reviewing some stuff from Newton's second law of motion. Remember that we have an equation for acceleration where we have the difference of our final velocity. Remember, f or v sub f is our final velocity, and our initial velocity is v sub I. So the difference of those, final minus initial, then divided by t in time and seconds, will give us our acceleration. And so for gravity on Earth, acceleration is always negative 9.8 meters per second squared. It's negative always because acceleration is moving down and not up. So this can be rearranged to solve for final velocity, right? So if we drop something and it's in free fall, it's going to hit the ground. It's going to hit the ground at some final velocity before it comes to a stop. So rearranging this equation, doing some algebra, gives us v sub f equals v sub I, so our initial velocity plus the product of acceleration due to Earth's gravity times time. All right. Yeah, we won't go over how it's rearranged, and you don't need to memorize this equation. We will always give it to you.
Yeah, let's go ahead and actually try this out. So the question is, what is the final velocity of an apple that starts at rest and then free falls on Earth for 4.2 seconds? So here's some things that we need to think about. Starting at rest is a velocity of what? Tell me in the chat box. If you're at rest, what is your velocity? In the chat, what is your velocity? Thank you, Amari. Thank you, Cody. Yeah, it's 0 meters per second. And since this is our starting velocity, should I label this as VI or VF? VI for initial or VF for final? Yeah, this is going to be our initial velocity. Starting or initial are the same thing, so this is our initial velocity. So that's going to help us out because we do need our initial velocity based on this equation. And it does say it's free falling on Earth, which means I need the acceleration due to gravity on Earth, which is our magic number here. You should, by the end of the course, know this by heart. It is negative 9.8 meters per second squared. We're going to see that get plugged in right here. Excellent. Yes, Jonathan. And we need our time. So what is the time up here? Go ahead and tell me in the chat box. Look at our annotations. Look at the things I circled so far. What is our time? Think about the units for time. Yes, I see Mallory in the chat. Let's get some more answers. Jaime, Cody. Yeah, so the seconds is our time. So this is what we're going to be plugging in for time. So plugging it in for my initial velocity, I should be plugging in 0. My acceleration due to gravity, I should be plugging in negative 9.8. Grab your calculators, just so you know, on your phone or in the chat, because you will need them for this question and the next question that you do on your own. And our time should be 4.2. Okay, so let's go ahead and take a look here. I need to do what first? Should I add first or multiply first? Should I add first or multiply first? You can also see I have parentheses to make it even clearer. Yeah, so we do what's in parentheses first, or we do multiplying first. Either way, that's the same concept. So tell me in the chat, what is negative 9.8 times 4.2? Grab your calculators, or you can Google what that is. Google will pop up a calculator for you. Grab a calculator on your computer or on your phone. So 9.8 times 4.2, and then make it negative. 9.8 times 4.2, make it negative. Thank you. I see Jaime, I see Mallory. Let's get some more participation. Again, we have one more question to do. We're almost out of time here, so work fast. Yes, exactly. So you should be getting negative 41.16. And I'm just going to pull down this 0 because it's just 0. And 0 plus negative 41.16 should still equal what? 0 plus negative 41.16 should still equal what? Tell me in the chat. Yeah, so our answer here should still be negative 41.16. Go ahead and give me a smiley face or an emoji in the chat box if that makes sense. So by the time this apple is done falling 4.2 seconds, it'll be moving at a speed of 41.16 meters per second in the downward negative direction, which is really fast. That's a pretty fast apple. All right. Excellent. This is going to be our answer for number 9. Make sure in your first box you put negative 41.16, and your second box you put meters per second. No meters per second squared, it's just meters / seconds as you see it up on the board, because this is a velocity, not an acceleration. Raise your hands for number 9. Again, make sure you understand this because you will need to do the next one on your own. Work fast. We're out of time. Let's go, go, go. I want to make sure we get that last question done. All right, let's go ahead and try the next one. All right, so we're going to annotate this one together. You do need to finish it on your own, though, so make sure that you have a calculator. Okay, so what is the final velocity of an egg that starts at rest, then free falls on Earth for 2.7 seconds? So taking a look here, starts at rest. That is my what? Is that my final velocity, VF? My initial velocity, VI, my acceleration due to gravity, or my time? Tell me in the chat box. Starts at rest. What is that going to be? Yes, again, this is our initial velocity starting, and that equals what? This is a number. If it's at rest, that equals what? Rest means what numerically? Yeah, it means 0 meters per second. All right, so we're going to plug in 0 here first. Excellent. What is our acceleration due to gravity? Again, it says it's free falling on Earth, so I need to know the acceleration due to gravity. What should I be plugging in underneath AG? What should I be plugging in underneath my acceleration due to gravity? Don't forget, gravity goes down, so it's a negative number that we should eventually memorize. Thank you, Cody. Let's get some more answers. Thank you, Jaime. Let's go, let's go. Need more participation in that chat. Thank you, Amari. Thank you, Kalina. Yes, negative 9.8. And what is our time? Again, time is measured in seconds, so what should I be plugging in for our time? Yes, right here, seconds. This is going to be 2.7, 2.7, okay? So remember, what we should be able to do now is we're just going to pull down this 0, right? And we should be able to multiply these together. Don't forget, your answer should end up being negative, because once you add 0, it still is negative. So you should have a negative number here. And your units, don't put answers in the chat. Your units should be meters per second, meters / seconds. For number 10, if you want to check your answer, we're in the Q&A area. You have 30 seconds to work on this one. And raise your hands. Go, go, go.
All right, great job, everyone. Today we learned how to differentiate between mass and weight. We learned about the effect of gravity that it has on objects in free fall based on Newton's second law. Remember that experiment with the bowling ball and the feather is pretty important to remember. To understand this concept, and then calculate. We learn how to calculate the velocity of an object in free fall. So tell us how you feel. Use your color pointers if you want. Tell us if you feel pretty good or awesome, or if you still need some help, which is okay. All right, awesome. So if you haven't already, again, just a reminder, please submit your quiz so that you get credit for both attendance and the notes. If there's anyone that still needs to stay behind for help, feel free to just hang around for a minute. Everyone else, have a nice day. I'll see you guys on Friday. See you again soon.